So now we want to look at 3A. We're going to do we're going to do all the steps. The particular products of the double exchange reaction between aqueous aluminum sulfate and aqueous sodium hydroxide show the full molecular formula, show the ionic equation, and in the net ionic equation, identifying all the spectator ions. So we're looking at problem 3A. All right, so first order business. A predicted products of the double exchange between aqueous aluminum sulfate. So I've already told you the phase of the starting materials. Otherwise, you'd need to look that up in table 4.1, the solubility table. So I'll start with aluminum, which I know to be Al. And aluminum's position in the periodic table gives it a charge of 3+. And then I want to do sulfate, and that was part of our information for our last polyatomics quiz, and that sulfate was SO4 with a charge of 2-. All right. So first thing we have to do is we have to exchange charges and subscripts to give balancing, and so this material is going to balance as Al2SO4, and then I need to put the entire polyatomic in a 3 in order to show I've got 3 of them. So I interchange charges and subscripts. Now, the phases are very important, and so I need to identify that this is an aqueous system. All right? So there's my aluminum sulfate. Now, I also have aqueous sodium hydroxide. And so I'll go up here in my place space. Sodium we know is Na with a +1 charge, and hydroxide is a polyatomic, OH- with a -1 charge. So I see the pluses and the minuses have canceled out here, so I don't have to take any balancing action. And so I get NaOH, and again I told you it was going to be aqueous. Okay. So that is the material there. Now, continuing, I tell you it's a double exchange, right? And a double exchange has a very particular meaning. A double exchange means the guys in the front stay in the front. So aluminum stays in the front, and sodium stays in the front. All right, and now I've got to interchange the back guys, leaving their subscripts behind. So the OH goes with the aluminum, and the sulfate, which leaves his subscript 3 behind, goes over and hangs out with the sodium. So that's my intermediates. Now, again, I need to balance everything electrically. Aluminum is still 3+. That hasn't changed. Hydroxide is still -1. That hasn't changed. Sodium is still +1. That hasn't changed. Sulfate is still 2-. And now I'm going to interchange charges and subscripts to create my product set. And so my product on the aluminum side is going to be AlOH3 in order to give me balance. And for the sodium material, he's going to pick up the subscript of 2 in order to give electrical neutrality with the sulfate, Na2SO4. Now, at this point, we need to flip back to table 4.1 and figure out what our phases are. So let's pop back to that table. Have it flip back in your packets. All right, and so we'll be looking up 2 things. First of all, we're going to look up aluminum hydroxide. And so I see in the table, hydroxide is in the lower 3rd quadrant here. Hydroxides are usually insoluble. Let's see if aluminum falls in the exceptions rules. And I don't see any aluminum up there. So the aluminum hydroxide material will be a solid. That's going to precipitate out. And the other material was the sodium sulfate. I see that sodium is soluble with no exceptions. I don't need to look any further. So now we have assessed the phases of the materials we just created. And so for the aluminum hydroxide, that's going to be a solid form. That formed a precipitate. And the sodium sulfate is also going to be aqueous, as the other 2 materials were. All right, so I exchanged. I created electrically neutral products. I assigned phases. What's the one step, Zaresh, that I'm missing at this point? What have I not done yet? I have not balanced, so I need to balance. Now, a couple of ways, a couple of strategies for balancing. Pick a large subscript. That's usually a good place to start. So as I look through my list, I see sulfate's got a 3 on it. So I'm going to start with the sulfates. I've got 3 sulfate on the reactant side, So I need 3 sulfate on the product side. So I'm going to go ahead and put a 3 in front of the sodium sulfate number. Now I like to kind of domino it with these things. So now I've got 6 sodium here. So I need 6 sodium on the reactant side. That gives me 6 hydroxides. In the product side, I've got aluminum hydroxide. I've got 3 hydroxides there. That puts me at 2 in that position. Check my aluminums, and I should be balanced at this point. So that is nicely balanced. So this is my overall molecular equation. 1, 6, 2, 3 are my coefficients. I've electrically balanced everything. I've done the overall balance. I've assigned phases. So this is the molecular equation. I'm going to call that just ME, the molecular equation. All right? So the first part of that's finished. Second part, make a complete ionic equation. So I'm going to take everything that's ionic and aqueous, and I'm going to break it up into its pieces, reporting both the charges and keeping track of mass balance. When things release their coefficients, their subscripts, that's going to become coefficients on the new guy. And solid materials we leave untouched. So as I look at my first material, I've got Al2SO43. I break that up, and it becomes 2Al3+. 2Al3+. I had 2 aluminums before. I still have 2 aluminums after the breakup. I report everybody's phase. So 2Al3+ aqueous. Now, I need to break up the sulfate. The subscript on the sulfate becomes his coefficient, 3SO4, 2-, and he's also aqueous. Note that I still maintain full mass balance. I had 2 aluminums before, I've got 2 aluminums now. I had 3 sulfate before, I still have 3 sulfate. Notice my original charge was neutral, and so the charge of these 2 pieces better be neutral. 2 times plus 3 is plus 6, and 3 times minus 2 is plus 6, so my charges are balanced. Yes, ma'am?
Why is it becoming a coefficient, not a subscript?
When the pieces break up, they move away from each other. So the sulfate, there were 3 of those surrounding that aluminum, and when I put them in water, they all just disperse. And so that's why the subscripts become coefficients, because these guys do not hang out together in aqueous solution. All right, let's break up the next piece. So I've got my 6 defines both of the pieces to come. So that means I've got 6 sodium with a +1 charge in the aqueous phase. Oop. Wrong symbol there. And I've got 6 hydroxides also in the aqueous phase. I'm trying to get it all on one line there. All right, 6 hydroxides in the aqueous phase. Mass balance is complete, charge balance is complete, everybody's got a phase. Now, on the product side, solids do not break up. So I simply report the solids. 2AlOH3 in the solid phase, unbroken up. Solids never break up. And finally, I got one last aqueous bit to break up. Now, a little complicated. I got a 3 coefficient on that sodium, and I've also got a 2 subscript. So when those pieces break up, I get 6 sodium pluses in the aqueous phase. And then that 3 distributes, and I get 3 sulfate 2- in the aqueous phase. All right, so all my mass balances should work. All my charges should be balanced. And this is my complete ionic equation. So let me separate one piece from the next. All right, so this piece here, the CIE, is the complete ionic equation. Okay, questions? How I go from molecular to ionic? Yes, ma'am. Yeah.
I think I just missed the last thing you did when I was still writing something. So that first part was the molecular equation.
Yes.
And then us breaking
it into pieces, ion pieces,
the ionic
is the complete ionic equation.
ionic equation.
Okay, we got one more to do before we're done.
One more part of this problem.
Yes.
Okay.
Yeah.
Okay.
Yeah, one more part. All right, so at this point we've got molecular, we've got complete ionic, and then the final part is we want to give the net ionic. And to create the net ionic, yes ma'am?
So on a test, are we going to have to write the, like, I forget what it's called, like 3 plus?
Okay, for me, 3 plus and plus 3 are the same number. I'll give you credit for it.
Yes.
Skynet, though, 3 plus and plus 3 are different. So you should have, for Skynet, you want the number in front of the charge for correctness.
Right, but on a quiz for the ionic equation, we still have to write charges.
Again, the name, ionic. Show me the ion pieces.
Okay.
Okay, that's the hint there. Now, the next part is we have to identify the spectator ions. We've got to pull the spectator ions out of this thing. Ciora, give me one spectator ion in this system. One species that's the same on both sides of the arrow. What do we see there?
The sodium?
The sodium, exactly. So the sodium, 6Na plus aqueous, is the same on both sides. That is a spectator ion. Do I have an additional one, Derek? The sulfates. So I got 3 sulfate ion on both sides. All right, so those are the spectator ions. They're not participating fully in the reaction. And so now I'm going to rewrite the complete ionic equation with the spectator ions removed. And so that gives me 2Al3 plus aqueous plus 6OH minus aqueous gives me 2AlOH3 solid. And we call this the net ionic equation. All right, so we have the full molecular equation. We have the complete ionic equation, everything broken up, and then with the spectator ions removed, we have the net ionic. Yes, ma'am?
Where did the sodium go?
It canceled out.
Oh,
On both sides of the equation. That's what spectator ions mean. Stuff on both sides cancel out. So that's what spectators do. We remove the spectators. They cancel out on both sides. Very good question. Now, I type all of that into Skynet, and I hit submit, and he goes, eh. What's wrong with it? This will happen to you on the homework. What is wrong with this equation? Yes?
Did you not write the charge on ALOH?
Solids don't show the individual charge piece because they don't break up. Thank you for participating. Somebody else? Tim, you have an idea? Anybody? Look at the coefficients. 2, 6, 2. Oh, we always present coefficients how? Reduced as far as possible. So the real net ionic equation for this problem will have the coefficients reduced all the way. So that's what Skynet and me want to see. Okay, so aluminum 3 plus 3OH minus aqueous gives AlOH3 in the solid form. And Skynet will accept that. Okay? So charges are balanced, masses are balanced. I remove the spectator ions. This is the net ionic equation. This is actually what's going on when you pour these two fluids together and you get a precipitation. Nothing else is reacting at all. Amelia?
In the molecular equation,
Yes.
how come you didn't need to put the SO4 on
The SO4 on the reaction side's right there.
on the product side? How come that didn't go in parentheses like it did in the?
Because I only had one. I only use parentheses around a polyatomic when there's more than one. Okay, so otherwise, parentheses is incorrect. I have one around the 3OH, but I don't have one around the 1OH.
Okay.
Okay, so that's going to be the issue for that one. All right. So that was a big, involved problem, but not something that is out of the realm. All right, let's look at 3B. Practice, practice, practice. Predict the products of the double exchange reaction between aqueous potassium sulfate and aqueous lithium hydroxide. show, as before, the full molecular equation, the ionic equation, and the net ionic equation. Identify the spectator ions. All right, so we're going to do the same steps that we carried out previously. So first I have to turn words into symbols. I've got aqueous potassium sulfate. Deidre, what is the formula? Aluminum sulfate. Oh, we're on the next one. Potassium sulfate. What's the symbol for potassium?
K, SO4.
K, and the sulfate's going to be SO4. All right, so those are the parts that make it up. I've got to balance it electrically. Tim, what is the preferred charge of potassium from the periodic table? Column 1.
+1.
Plus 1. Okay. Sulfate. Sarah Christopher. Polyatomic ions. -2. Okay, so as written, it's not balanced. I have to interchange charges and subscripts. So that's going to give me K2SO4. And I told you it was aqueous, though if we looked it up, we would get the same information because it's potassium. Potassium is always soluble for the work we're going to look at. Next part we're going to add in, Sarah Martin, we're looking at sodium hydroxide. What's the formula for that? Symbol for sodium?
Sodium
Na. Symbol for hydroxide?
Na.
OH. Charge of sodium based on its position in the periodic table? Plus hydroxide?
Actually,
What did I do?
It's
lithium hydroxide.
Oh yeah.
Okay. That was like,
That was why you're going like, what's he talking about? I'm looking at the previous problem. All right, lithium. Fortunately, lithium's also in column 1, also +1 charge. So that one's already balanced electrically, so I don't need to take any additional action. That's just going to be LiOH. Again, lithium is always soluble for our work, so I got 2 pieces. Next up, I told you it's double exchange. So in a double exchange, the guys in the front stay in the front, leaving their coefficients, their subscripts behind. So I write the K in the front position, I write the lithium in the front position, but I do not bring the 2 over from potassium. The sulfate and the hydroxide exchange partners. So the hydroxide goes with the potassium, the sulfate goes with the lithium. All right, now I need to electrically neutralize everything. Charges up top are still the charges. K is still plus, sulfate still 2 minus, lithium still +1, hydroxide still -1. KOH is fine as it is. Lithium sulfate, however, I need to interchange charges and subscripts. That gives me 2 LIs. Okay? And now, good work product removes these charges here. Keep it nice and clean. And now I need to balance everything electrically. All right, so I've got 2 potassium, so I might start there with the 2 in front of the potassium. That gives me 2 OHs, so I need a 2 in front of the lithium hydroxide. That gives me 2 lithiums. That's set. Check my sulfates, I'm good to go. And so that works. Okay. Now, phases. Back to my chart. I'm looking up 2 products. Potassium hydroxide. Madeline, soluble, yes or no? Yes. Lithium sulfate. Ashley, yes or no? Soluble. Lithium, always soluble. Potassium, always soluble. Sulfates, always soluble, except some exceptions which are not listed. So in this case, everything is aqueous. Everything's aqueous. This is my molecular equation. Right now, next up is I've got to convert that into a complete ionic equation. So I'm going to take all the aqueous ionic pieces and break them up. K2SO4 aqueous will become 2K plus aqueous. Subscripts become coefficients when the pieces are released. Plus SO4 2 minus aqueous. Okay, we broke up the first piece. Second piece. The 2 of the lithium hydroxide defines both of the pieces that will follow. 2Li plus aqueous plus 2OH minus aqueous. At this point, I have maintained mass and charge balances. Right, everybody good so far? Yes, ma'am?
Why is it 2OH again?
Oh, the 2 defines everything that follows. So I have 2 lithiums and 2 hydroxides in the problem. Okay, good question. Now, on the product side, KOH, break that up because it's aqueous, gives me 2K plus aqueous. Again, the 2 defines everything in the compound, so that gives me 2 hydroxides, aqueous. And now I want to break up the lithium sulfate because he's also aqueous. The subscript of the lithium becomes his coefficient, 2Li plus aqueous. And then the sulfate, there's no coefficient, coefficient 1. There's no subscript to worry about. So he's just plain SO4 2 minus aqueous. All right, and this is my complete ionic equation. Yes?
So the molecular equation, you don't write the charges.
The molecular equation does not report the charges. That's the difference between the two. No charges in the molecular. Everything's a neutral compound. The ionic lifts the curtain and shows what's going on behind the scenes. Okay, so that's the difference between the two. Right? Now, we need to remove the spectator ions. So Maggie, is there a spectator ion in the complete ionic equation we can identify?
You have sulfate.
The sulfates. So the sulfates are spectator ions. Okay. Kennedy, any others? The potassiums. Potassiums go away. Allie, anything else? The hydroxides. Kyle, anything else? The lithium. Oh, everything is a spectator ion. And so now, when we write the net ionic equation, what's left over? Nothing. When you encounter this in Skynet, and you will, the answer is no reaction. And he will provide that as one of your choices. No reaction. So don't be fooled. Now, why is there no reaction? Because nothing precipitated. Look what we've got. The molecular equation suggests double exchanges going on, people switching partners. But in reality, everything is really just floating around doing its own thing. I had 4 floaties in the first half. They might bump into one another. Oh, excuse me, sorry to have bothered you. And then they float away. So there's nothing happening from a reaction point of view here. Why? Because every species was aqueous. If that's the case, the net ionic equation will always be no reaction. Questions? Yes, ma'am?
In the molecular equation,
Yes.
where did the 2 in front of the Li come from in that first line that you have up?
I have lithium balance. For my product, I've got Li sub 2. That means there's 2 lithiums on the product side. I must also have 2 lithiums on the reactant side.
Okay.
That's where the 2 comes from. That also defines the OH. You'll notice I got 2 OHs there and also 2 H's on the bottom.
So then when you go to write the complete ionic, you have to refer back to...
Absolutely. Again, if there were 2 in the molecular, there will still be 2 in the ionic. But when they break apart, the K pluses don't hang out. They go do their separate thing. So it's not K2 plus, it's now 2K plus. They separate. All right? So again, it's a marriage. The marriage fell apart. After their divorce, they still don't hang out. Okay? There you go. So that's why the 2 defines everything that follows. Okay? Yes, Sarah?
So you said there's no net ionic equation because
everything's a spectator ion. Everything canceled out in the complete ionic equation.
yes, is that because they're all aqueous?
Because they're all aqueous.
Now is it specifically aqueous or because they're all the same phase?
Well, again, what we're looking at, it's that everything is in both positions, in both reactant and product side. And that's what makes them cancel out.
Yeah.
Why we show it the way we do with the ionic system is it is aqueous, and that allows us to break things up into ions. If I have table salt on the bowl in your kitchen, that stuff is solid. It is not possible for it to break up. When you put it in water, though, then the water solubilizes it, and now the sodium's float away and the chlorines float away. So you've got to have water as the solvent to get it to break up. But once it's broken up, you eliminate the pieces that are on both sides of the arrow.
So if they were, say, for some reason they were all solid.
Then all you would have would be the Me. There would be nothing else going on. Because I can't create ions without the aqueous part.
Okay.
Okay? Yes?
So for it to be a spectator ion, does it have to be like identical?
Every detail has to be the same.
Okay.
2 pluses, Ks, charges, phases. Okay? Yes. Everything got to be the same to cancel it out. Yes, ma'am?
I'm sure this is the last question for this problem. For the answer, is it, so for the complete ionic equation, is all of those lines is all the answer?
Yes.
Not just what's
You need
active?
everything. You need reactants and products. Again, this is the case where there's 75 keystrokes.
Okay.
And if you miss one keystroke,
Okay.
wrong. Now, on me, I'll be more generous. Oh, they forgot blah, -1. Where Skynet is wrong, 100%. Okay? All right, that was a big question. Lots going on. Important to note what was going on with that one. So we spent 30 minutes doing 2 questions. Think about that in our upcoming test.
Right? That's
Yeah.
not bad.